Hello ladies and gentlemen, today we're going to learn about Atwood machines. So an Atwood machine is a system that a scientist named Mr. Atwood designed so that he could study the motion of objects. What I'm going to show you today are two different versions of Atwood machines. One is a pulley system that looks somewhat like this, and another one is a system where we have a mass on a table connected to a pulley and another mass that is hanging off the table, like so. Now, when I do these problems, I'm going to show you how to solve them without any numbers, with a reminder that you can use this method to solve any Atwood machine problem. All you have to do is set up the equations like I did and plug in numbers and find out the variable that you're looking for. Okay? So the first one I'm going to work on is the regular Atwood machine. And I'm going to call this mass 1. I'm going to call this mass 2. Okay? And for all intents and purposes, this is a string. This is a pulley, and the strings and the pulleys are massless, meaning that they don't have any weight. Okay, so I will also say that mass 1 is going to be greater than mass 2. So if this were like a video, for example, and we push play, we would see the mass 1 move down, and we would see mass 2 move up, like so. Okay. Now, when we solve these Atwood machine problems, I want you to set up the pulleys so that it lies in a horizontal direction. Now, what I mean by that is I want you to swing everything up this direction, and I want you to swing everything up in this direction. Now, I don't mean to actually swing the masses on a pulley, but to imagine it. For example, it would, if I were to quote-unquote swing everything, the new system would look like this. Okay, and this will be mass 1, and this will be mass 2. Now, the reason why we do this is because when we're creating our net force equation, the math becomes a lot easier. All right. So first things off, I want us to create a free body diagram for each of these masses. So the first thing, we have mass 1 going down with the force of gravity, and we have the weight of mass 2 going down with the force of gravity. We have the force of tension in the string there. And we have the same string over here with the same force. Okay. Now I'm going to redraw this scenario, but with the flipped up version. Okay. So I'm going to have my pulley there. I'm going to have my first string, my mass. Okay. This is going to be mass 1. This is going to be mass 2. Now, because I swung everything up, my force of gravity will be in this direction, and I will call that mg, and mass of 2 times gravity. And because I swung everything up in this direction, I'm going to call this m1g, or the weight of mass 1. And this will be the force of tension, and this will be the force of tension. Okay. Now from there, I will designate anything going to the right as positive. Okay. So if I were to create my net force equation, it would look like this. So the sum of the forces is equal to the masses times the acceleration. Okay. So normally when we write these equations, we will write it like this, right? But now we're dealing with more than one object. Because we're dealing with more than one object within this system, okay, we're dealing with 2 objects, we have to take into that into account. So instead of just ma, it would be m1 plus plus m2 times a. All right. Now let's create our net force equation. I'm going to add up all the forces. We're going to say this is equal to m1 plus m2 a, and all of that is equal to negative m1g, negative because it's going to the left, plus f of t minus f of t because it's going to the left, plus m2g. Okay, and I'm going to clean this up a bit. Our net force equation is equal to the sum of all the forces, which is the sum of all of the masses. These two cancel out, so we are left with the weight of mass 1 plus the weight of mass 2. Okay, now that is the general setup. From here, you can rearrange the variables to get what you need. For example, if you're looking for acceleration, it would look like this. Acceleration is equal to negative m1g plus m2g, all divided by m1 plus m2 times m1 times m2. And we got that by dividing both sides by the sum of the masses. Okay. Now, another type of problem that I could ask you is, I want to know what the tension is. So in order to find the tension, what you have to do first is understand that if we look at the system as a whole, you saw that the tensions canceled out. So what you have to do is take a look at one part of the Atwood machine. Okay. So with the acceleration that you just found out, because that's the acceleration of the whole system, okay, we have to plug that into a new net force equation looking at only one of the systems. Okay, so I put a dotted line around this to make things easier. I'm going to put the same dotted line around this as well. Okay, that's my new system. So if I'm going to write a net force equation for my new system, it'll be the sum of the forces is equal to mass times acceleration. And this time we're only going to put one mass, m1, because that's our new system that we're looking at. Okay, is equal to, remember, we said that anything going to the right will be positive, so that would be mass 1 times g negative plus f of t. All right, and from the acceleration that you found before, you're going to plug that in here. You're going to plug in your value for mass, and the value for acceleration due to gravity, and you can find f of t. So what it will look like is, let's clean this up a bit, m1a plus m1g, so I just added that to the other side, is equal to f of t, or, okay? So the steps are, first find your acceleration, and then isolate a part of the system that has a tension, and then create a net force equation and solve for the tension. All right? Now, the second type of Atwood machine problem, okay, is a pulley on a horizontal surface. So I'm going to call this M1. We have a string, we have a pulley, and we have M2. Okay, this will be my table. Okay, so this is my entire system. Now, the same tricks go for this. All right, what you want to do to start you off is create a free body diagram. Okay, so I'm going to start with M2. So we have the force of tension going up, and we have the weight going down. All right, we have the force of tension along the rope going to the right. We have the normal force pointing up, and we have the weight of block 1 going down. Now, remember my trick. Try to make everything along the same axis. So because this is already horizontal, I'm going to swing this up like that. Okay, I'm going to swing everything that I just wrote here into the horizontal axis. All right, and so I will get something that looks like this. Now from there, creating your net force equation is really simple. I'm going to create one for the x and the y. So we know that the sum of the forces, let's say for the x, is equal to the masses, so we have m1 and m2, times the acceleration, okay, because acceleration is shared by the entire system, is equal to, so here you have to take a look at what's along the x-axis. We have, and of course, everything going to the right is positive, so we have positive f of t minus f of t plus m2g. Okay, so as you can see here, the entire system is being dragged by the hanging mass. Right? Now, the net force for the vertical component would just simply be this normal force plus this weight. Alrighty? Okay. Now, the cool thing here is that this entire thing will actually add up to 0 because when this mass was hanging down below, I'll redraw that. When this mass was hanging down below, like so, okay, this object doesn't move in the up or down direction. So because m1 doesn't go in the up or down direction, your net force for the y direction will be 0. Okay, so the only equation you have to worry about is the f of x net force equation, which I'll rewrite like this. Ft minus f of t plus m2g is equal to m1 plus m2 times a. All right, so notice how I didn't use any numbers because I want you to focus on how to solve these problems, the basic skeleton, the basic blueprint. All right, give it a go, and I'll see you all in class where we will practice labs using Atwood machines. Thank you.